Welcome back to Mechanical Engineering Made Simple. Imagine designing a massive, incredibly expensive machine, right?
Yeah, something that's perfectly balanced.
Exactly. It's precision engineered, bolted securely to a thick concrete floor. And the moment you turn it on, it spontaneously decides to tear itself to pieces.
Which is absolutely terrifying to watch, by the way.
Right. There are no external earthquakes, no bumpy roads, no broken parts. The machine literally destroys itself using its own momentum.
And this is the invisible battle happening all around you every single day.
It really is. I mean, it's happening in the laundry room right now. It's happening under the hood of your car. And it's even happening deep inside the hulls of massive cruise ships out on the ocean.
Absolutely, it's everywhere.
So today, the mission for this deep dive is to explore this hidden, often destructive world of mechanical vibrations. We're going to look at two specific things today.
Right, the core problem and then the solution.
Yeah, first, this terrifying phenomenon called self-excited vibrations, where a machine basically becomes its own worst enemy. And second, the absolute genius engineering tricks like dynamic absorbers and dampers that engineers use to save them.
It's a really fascinating area of physics.
It is. So if you've ever wondered why your washing machine doesn't just walk out the front door, you are in the right place.
It really is a battle, and to understand how we fight it, we first have to distinguish between the two main types of vibration that engineers worry about.
Right, because they aren't all the same.
Exactly. Most people are very familiar with forced vibration. Think of driving your car over a bumpy, unpaved road.
Or, having an unbalanced wheel on your car that shakes your steering wheel at a certain speed.
Sure, that's a perfect example. In a forced vibration, the alternating force that is shaking the system exists entirely independently of the motion.
Meaning, if you magically grab the car and hold it perfectly still, that bumpy road is still there.
Right.
The external force hasn't gone away at all.
Precisely. But self-excited vibration is a completely different beast. In a self-excited vibration, the alternating force that sustains the motion is actually created by the motion itself.
Oh, wow.
Yeah, if you stop the motion, the force entirely disappears.
Okay, let's unpack this, because that sounds almost like magic. I mean, how does a vibration feed itself without an external force?
Well, to understand it, we really need to look at the physics of what we call negative damping.
Negative damping, okay.
Yeah. If we look at the characteristic equation of a damped-free vibration...
Oh, here comes the math.
I'll keep it simple, I promise. It's just mx double dot plus cx dot plus kx equals 0.
Right, the classic mass spring damper setup.
Exactly. So in a normal system, that damping coefficient, the c, is positive.
Which means the vibrations naturally die out over time, right?
Yes. But if a physical mechanism causes that c to become less than 0, the exponential factor becomes positive.
Wait, so the machine, starting from almost nothing, just oscillates with an ever-increasing amplitude.
Exactly. It just builds and builds until something physically breaks, or some extreme restraint limits it.
So it's kind of like pushing a child on a swing.
That's a great analogy, yeah.
But imagine the swing itself is somehow generating the pushes from its own momentum.
Yes. The motion literally creates the push.
But wait, how does a lifeless piece of metal just decide to create negative damping? I mean, a spinning shaft doesn't have a little motor deciding to push it.
No, it doesn't.
So where is the energy coming from?
It hides in tangential forces. And a classic example from the sources we're looking at is called hysteretic whirl.
Hysteretic, like hysteresis, the internal friction inside the material itself.
Spot on. When a solid metal shaft bends and rotates at high speeds, the metal fibers on the outside of the bend are constantly stretching.
And the ones on the inside are compressing.
Right. Because of internal friction, the metal doesn't perfectly and instantly bounce back. There's a slight phase shift, a delay, between the strain, which is the physical bending, and the stress.
The stress being the internal force trying to snap it back straight.
Exactly. So the resulting elastic restoring force isn't perfectly parallel to the deflection.
So it's essentially getting tired and lagging behind its own rotation.
Yes. And that sideways angle creates a tangential component that pushes the shaft forward.
Causing a forward whirl.
Right. A forward whirl that just builds and builds.
Wow. So the machine is basically cannibalizing its own rotational energy to push itself sideways. That is a dangerous loop.
It's extremely dangerous.
But so far, we're just talking about tired, solid metal. What if the machine isn't solid? Like, what if we're dealing with a hollow rotor?
That introduces a whole new variable.
Fluids.
Yes.
Yeah.
Trapped fluid whirl is another major culprit. Think about high-speed centrifuges with liquid trapped inside hollow spinning rotors.
Hold on, that doesn't make sense to me. If I take a bucket of water and swing it in a circle, centrifugal force just pins the water flat against the outside walls.
Yeah.
So shouldn't the liquid just pool outward radially and balance itself?
You would think so if the fluid were perfectly frictionless. But you have to factor in viscosity.
Oh, right. The fluid is sticky.
Exactly. The spinning surface of the inside of that hollow cavity isn't totally smooth to the fluid. It actually drags the viscous fluid along with it.
Creating an angle of advance.
Yes, so the fluid doesn't just pool straight outward on the heavy side, it gets dragged forward.
Oh, I see. Because the heavy pool of fluid is now physically leading the deflection.
Exactly. So its centrifugal force isn't pointing straight out either. It has a tangential component pulling the rotor forward.
Pulling the machine off its axis.
Right, creating a forward whirl once again. But perhaps the most violent example isn't from fluids or internal metal fatigue.
No?
It's from external contact. Dry friction whip.
Dry friction whip. Okay, like what happens when an unlubricated shaft rubs against a stationary stator?
Yes, like if a massive steam turbine shaft sags just enough to touch the steel housing. What's fascinating here is the direction of the destruction.
How do you mean?
Well, when the rotating shaft makes contact with the dry stator, Coulomb friction creates a massive tangential force. But think about the geometry of two circles touching.
Okay.
If a shaft is spinning clockwise and it rubs against the inside of a stationary ring, the friction actually causes the shaft to roll along the inside of that ring.
Oh, like a gear meshing.
Exactly.
If you picture a clockwise spinning gear walking around the inside of a larger ring gear, it walks counterclockwise.
Exactly like a gear. The friction drives a whirling motion that is backward counter to the direction of shaft rotation.
And that is a catastrophic feedback loop. The harder it rubs, the harder it pushes itself backward,
Which increases the centrifugal force.
which makes it rub even harder into the casing.
Right. Real-world turbines have literally ripped themselves off their mounts in seconds because this dry friction whip melts the metal.
It just causes the rotor to explode through the casing. That is wild.
It really is.
So what does this all mean? If machines naturally develop these destructive tangential forces, engineers must have a way to fight back. I mean, we can't always just make the metal thicker.
No, eventually things get too heavy to be practical.
Right. So how do we kill the vibration?
This brings us to the second half of our mission, dynamic absorbers. And the first defense is the tuned, undamped dynamic absorber.
Okay, an undamped absorber.
Yes. The concept is incredibly elegant. If a system is being forced to vibrate at a constant frequency, you can just attach an auxiliary mass on a spring tuned exactly to that same frequency.
A sacrificial mass. We intentionally attach something else to the machine just so it can vibrate instead.
That is the goal. This auxiliary mass enforces a node.
Enforces a node. What does that look like in practice?
It means the small attached mass ends up vibrating violently. It creates a reaction force that perfectly cancels out the excitation force.
Leaving the primary machine sitting dead still.
Precisely. The expensive tool you care about sits dead still while the little mass hidden inside goes crazy.
You know, this makes me think of high-end electric hair clippers.
Oh, that's a great example.
Right, because they operate at 120 hertz from the power supply.
Mm.
The cutter blade is moving back and forth incredibly fast, generating massive unbalanced forces.
But if they place a precisely tuned mass spring system inside the handle,
The internal mass takes all the punishment, it vibrates wildly, and the clipper handle stays perfectly still in your hand.
it's a perfect application because the wall power never changes its frequency.
But wait, this only works if the frequency never changes.
Right.
What if
Yeah.
the machine speeds up or slows down? I mean, doesn't the absorber become a massive problem then?
That is the exact fatal flaw of the undamped absorber.
Really?
Yes, an untuned absorber splits the system into two completely new natural frequencies.
Oh no. So instead of having one speed where the machine shakes itself apart, you've just doubled your chances of hitting a resonance point.
Exactly. If the machine speed varies, it will hit one of those new resonances and vibrate worse than before.
Okay, so building on that realization, how do we protect machines that do change speeds? Because washing machines, car engines, they speed up and slow down constantly.
That's where we move to systems that dynamically change their tuning. Let's look at the home washing machine spin dryer.
Oh yeah, when a load of wet clothes is unbalanced, the basket wants to tear itself apart as it speeds up through its critical speed.
To stop that, engineers use a fluid or ball balancer.
like a hollow ring at the top filled with viscous fluid or metal balls.
Yes. Now, below the critical speed, the fluid pools on the heavy side.
Wait, on the heavy side, doesn't that just make the unbalance significantly worse?
It absolutely does. Below critical speed, it increases the vibration.
Then why use it?
Because as any rotating system passes through its critical speed, it undergoes a massive 180-degree phase shift.
The phase shift.
Yes, it stops rotating around its geometric physical center and starts rotating around its center of gravity.
Oh, so the heavy wet towel is suddenly pulling the physical center of the drum toward the center of gravity.
Exactly. And because the axis of rotation shifts, it causes the fluid or balls to move to the completely opposite side.
Which perfectly neutralizes the unbalance.
Right.
That is brilliant because it's completely self-regulating.
Exactly. The physics just automatically fling the counterweight to the correct side.
But what about torsional vibration, like in car engines? Engines constantly change RPM, so a fixed spring is useless. How do we tune an absorber to a moving target?
Well, if we connect this to the bigger picture, we find the pendulum absorber.
A pendulum, inside a spinning engine block.
Yes. You attach a pendulum to a spinning crank hub, and because centrifugal force increases with the square of the rotational speed.
Wait, so the invisible spring holding the pendulum magically gets stiffer as the engine revs higher?
Exactly. Its natural frequency increases perfectly in sync with the engine's speed.
Wow. So it's completely self-tuning.
Right. It neutralizes specific orders of vibration, like the 4.5 order in an engine, rather than a fixed frequency. The pendulum just wiggles back and forth, absorbing all the energy.
Saving the crankshaft from snapping in half.
Precisely.
Okay, here's where it gets really interesting, so I want to scale things up. We've talked about hair clippers and washing machines. What's the biggest vibration problem we can solve? What about a massive ship rolling in the ocean?
For ships, we use anti-roll tanks. They act as giant auxiliary mass dampers.
So like giant wing tanks on opposite sides of the hull.
Yes, connected by massive pipes. And water sloshing between them acts as a tuned mass.
I assume the flow is restricted by valves, right?
Yes, to provide precise damping. By tuning that sloshing delay, you create a massive counterforce.
So the water arrives late. When the ocean tries to push the ship back, the thousands of tons of water are still trapped on the other side, dragging the ship heavily back upright.
Exactly. On the German luxury liners Bremen and Europa, these exact tanks reduced the maximum roll from 15 degrees down to just 5 degrees.
That is incredible. But that's a completely passive system, right? Just relies on gravity. Can we do better than just waiting for water to slosh back and forth?
We can. We move to activated vibration absorbers. Massive gyroscopes can be precessed by motors.
Precessed, meaning physically twisted on their axis.
Yes. An activated system uses a servo mechanism. When a sensor detects even a fraction of a degree of roll, a servo motor actively twists the gyroscope.
Oh, and when you twist a spinning gyro, it fights back at a 90-degree angle.
Exactly. It exerts maximum stabilizing torque instantly.
So it totally overrides the ocean's attempts to vibrate the hull. You're using an intelligent machine to combat the raw forces of nature in real time.
It's engineering at its finest.
It really is. So we've gone from a lifeless piece of metal vibrating itself to death, all the way to massive servomotors actively twisting tons of spinning steel to calm the ocean. Let's tie it all together for you listening.
Yeah, let's do that.
Whether you're trying to figure out why a piece of machinery on your workbench is humming uncontrollably, designing a new power tool, or just appreciating the invisible physics keeping your washing machine from destroying your laundry room, understanding how to balance these forces is literally like having a superpower.
It changes how you see the world.
It does. You realize you don't always have to fight the energy directly with thicker walls. You can redirect that destructive energy into a harmless sacrificial mass.
You can tune the system to effectively fight itself. And, that concept goes far beyond mechanical engineering.
How do you mean?
Think about your own life and workflows. Where do you have self-excited, negative feedback loops that feed on their own momentum?
Oh, wow.
And what kind of auxiliary mass or mental dampener could you creatively introduce to absorb that destructive energy before it shakes your foundation?
Master the critical few, or the trivial many will master you.
Mm-hmm.
If this episode gave you a solid takeaway, drop a comment. It takes you a few seconds, but it tells me this workbench is worth keeping alive.